Good morning, Holly. Good morning, Josh. I thought that I've been working through this condensate drain trap recommendation. I think I've about got it. So we'll see. It's got a few moving parts. So I thought I might just record a Zoom video and send this along with the files to you to help you in your efforts to write this up. So where shall we begin? I think maybe the hobo file is not a bad place. Get myself out of the way here. I don't know why I did the camera. We've been doing Zoom stuff with meetings at the ME department, and we always use the camera on those, so I've gotten kind of used to it. So anyway, so what we see here, this is the composite file, and I've been monkeying around with this thing. So let me put it back together a little bit here. Let's get the whole data set in here. It takes just a second to get this thing positioned. Sorry, I should have had all this ready. There we go. That's pretty good. And let's see. Yes, let's shrink up the current and shrink up the PSIG a little bit. Okay, so the pressure traces are at the top. You can see those moving. And I'll move the current down a little bit towards the bottom. There we go, just so you get a little separation. Okay, so these are the upstream, downstream pressures. These are the currents. We actually have 4 air compressors. So then what I did is I used the averaging tool up here, and I averaged it for, I just kind of picked 2 spots. I got about 5.5 days, so a little over that. And then I'm displaying over here on this side for the amps on the compressors. There's the Curtis IR. It says GC. It's supposed to be GD for Gardner Denver. Hit the wrong key. Sorry. And there's 2 Gardner Denvers, left and right. So you can see min, max, and average current for each of these compressors. And so this is where the numbers come from. And I've got a little spreadsheet I'm going to put up here and show you in a second. This file is on the Google Drive, and hopefully you guys both have access to HoboWare these days. I'm not sure where all that shook out, to be honest with you. Okay, so let's put the HoboWare down, and here's the spreadsheet. Okay, and like I said, I'm going to send this to you. So I start off up here just telling you the length of time that we logged, a little over 5.5 days. And here are the 4 compressors, and this was the maximum amps. And so I am inferring that maximum amps would be full capacity on the compressors. Now they're all 200 horsepower. The Curtis is a little shy. I don't know if it really loaded to 100% at that or not, but it doesn't really matter. The reason I'm doing all of this initially is to figure out what's their average cost of compressed air generation. And we will use that in the calculations of savings when we go to the zero loss drain traps and get rid of at least 4 of their timed drain traps. They have 4 of them at one location that are manifolded together. And I'll show you pictures of some of this in a little bit. I don't have a great picture of all 4 of them, but they were. And when you look at the timer settings on all of them are to blow 10 seconds and be off for 30 seconds. So that's a 40-second cycle. And so the 10 seconds that it's on divided by 40-second cycle time, that's 25% of the time this thing's blowing. And they've got 4 of them manifolded together. So that means that that's equivalent to having one of these things blowing continuously. So this is a 7/8 inch leak all of the time. And so the numbers turn out to be fairly significant and they really do. They can put 1 0 loss trap on this entire coming off of the manifold that's receiving the flow from all 4 of these, and it'll reduce the amount of air loss as long as the trap's working right. They won't lose any air. So this is significant. It's I think I'm right now about 176 CFM, but we'll get there, of savings. That may be enough to keep that Curtis from starting. At least the Curtis doesn't start all that much. And if this is pretty much base load, it will reduce the runtime on the Curtis, which would help, because when the Curtis jumps in, it upsets the system, and we start getting pressure fluctuations and all that sort of thing. It does shut down on its own, but it's more maintenance, wear and tear, I think, than actual energy. But nonetheless, we've got good savings to get rid of this. At least what's being blown through these 4 traps, and the economics are good because you're going to basically get rid of 4 time drain traps with 1 0 loss trap. Well, that's 4 to 1 bang for the buck. That's pretty good. Now they have some other traps which they probably ought to get rid of, and I think what I would do is I would write up the 1 to get rid of the 4, and just say in there they should probably remove the other traps as well. I'm not sure how many total that they have. Okay, enough general BS here. Okay, so these are maximum amps, and so I just totaled them. And that was from the data file. That's not nameplate. That's what we actually measured, at least during that 5.5 days. And this is average current. Okay, so the total that we, if I just pick the peaks out of those files, it's 873 amps, and the average over that 5.5 day period is 339. Okay, so I'm going to swag that all of these compressors have the same capacity. That's not going to be 100% true, but they're all 200 horsepower, so it's going to be pretty close. So I'm going to use 850. And so if I take 850 times 4, I get 3,400 CFM for total capacity if all 4 compressors run fully loaded. My current, my 339 divided by 873 is about 38.8%. And so I'm going to say I'm getting 38.83% of 3,400 for my compressed air generation. No, that's not perfect, and you know, we could make tweaks and adjustments, but it's ballpark, and that's really what we're looking for here. Just, you know, a good ballpark estimate. Okay, we're going to have to calculate power. So my recollection is from some of the measurements that we took that the voltage runs someplace in the neighborhood of 480. So I'm going to use 480 instead of 460. And so just into the power calculation, that's going to be my 339 amps times 480 times the square root of 3, and I use 0.8 for a power factor because not all these machines they're fairly well loaded. Sometimes they're lightly loaded, you know. So overall I use 0.8 and I get 225.47 kW. So that's the power on those, the average power draw for the compressors. This then is how much air is produced during this 5.5 day period. So I take the 1,320 CFM times the number of minutes and just divide by 1,000. And so you can check the math, but I think that's correct. And so we got about 10,509 units of 1,000 cubic feet produced during that 5.5 day period. I went to the utility file and pulled the blended cost of electricity. I'm just, you know, this is a little bit rough and dirty, but I'm not going to get into demand and consumption on this. And how much of this you tell Rutgers, I'll leave that to your judgment, because you guys are the ones that got to get it approved. Anyway, I mean, I think for this calculation, the blended is fine. Okay, so then the electric cost, well, that's that 225.47 kW times the number of hours in that 5.5 day period times the electrical rate, and I'm getting $20,068. And so then I take that $20,068 and divide it by 10,509 units of thousands cubic feet. And each one of those cost about a little less than 20 cents to produce. Now that's on the production side. Now, if we reduce compressed air use, because the compressors don't unload perfectly, we don't get all of the cost of generation back as savings. So I have estimated 60% as the amount that we'll actually save. And I'll show you where that comes from here in just a second. But so of this 19 cents, I take 60% of it, and I get a little less than 12 cents per 1,000 cubic feet. So if we save 1,000 cubic feet, I'm saying that's going to save us, not quite 12 cents. Okay, that's how I'm going to do the savings calculation. Okay, let me jump to the PowerPoint here. This is the PowerPoint that I made for SHOT way back. I think I copied you guys on this. You guys have probably seen this. We can go back to the beginning of it. I've stuck some new slides on the end of this. But so you see this, and this was stuff I sent them before. Just, I don't know, I got enthusiastic one day. Showing them their pressure drop across the system, which is very good, 2 psig. This is what happens when the Curtis compressor starts, and we get these pressure transients. It looks like a load unload situation. I'm not sure. Generally speaking, we're VFD control, but that obviously doesn't look like VFD control. And so you get some kind of an idea. IR, let me move my picture here so I can read my slide. Now I'll put myself down here for a little while. So the red is the Ingersoll Rand. It stays fully loaded. Let's see, the kind of purple one or magenta down on the bottom portion. That's the Gardner-Denver left side compressor. And that's the one that runs quite a bit. The other Gardner-Denver was basically off. And then you see the Curtis kind of jumps in and out a little bit. About 25% of the time, the Curtis compressor is operated very lightly loaded. My estimate when I looked at just at the Curtis itself was about 120 CFM reduction in loads and demand could eliminate that Curtis. And so, just on this drain trap, I'm up 176, I think, is the estimate. So I think it's going to help this Curtis starting and stopping, and then that's something that can be discussed in the report as well. This shows typical operation. Much of the time, 2 compressors is sufficient. So when the black goes away down here, then we're just on these 2. And you can see here, there's a period, I don't remember what days, this may be a weekend, I'm not sure. But at any rate, this left side, Gardner-Denver, was lightly loaded. This guy was carrying most of the plant by itself. So, another issue there, perhaps this Gardner-Denver could be put on automatic start-stop, and for periods such as this, when we get these drain traps changed out, that might be enough to eliminate the need for this. And that would be significant. I mean, that's a 60, 70 amp load that maybe could be shut down a bunch of times. So that's something else that could be discussed. I don't know that we can quantify that. Let's see, in this 8-hour period when demand was high enough to keep the Curtis cycling on, cycling on and off, these short cycles cause maintenance. Yeah, so you see all that wear and tear on the Curtis. That's just a detailed. So you see when this thing loads and unloads, I mean, it's not it's not terribly long. I guess this period. You can look at this and get in the file a little bit. Yeah, so from here to here. So this was, I guess, an unload period because the current fell. No, I take it back. Let's see. Now, I'd say no. This was operating. So this thing operated for looks like about 3.5 minutes, producing air, and then it dropped down. I guess on the VFD, and then it came back. So anyway, this is a detailed look upstream pressure, the Gardner-Denver compressor room. Again, the pressure drop is good. So you can look at this. Kind of went on and on about that. Okay, so the reason I wanted to get to this is there's 2 slides here that are cut out of my compressed air presentation. And this is the one that shows these compressor control qualifiers. And so basically what that is, that's the percent of the cost of generation that you save if you reduce air demand for a compressor that's has that type of control. And so that's why that's why I use that 60% for on this variable speed situation. Okay. All right. And that's a little example. If you want to study up on it a little bit, I stuck that in. This shows the time drain traps. There's an Ingersoll Rand, and basically they're set to blow. This is a blow up of a different trap. This is a different manufacturer. These are the one on the left. That's the one that's the 4 of them are manifolded together, but you can see very clearly that that thing is set to be on for 10 seconds and then off for a half minute, which is they're blowing it as much as they can blow it. So we got 30 seconds off and then 10 seconds on and 30 seconds off and 10 seconds on. We got 4 of those all strung together, blowing into the same pipe. Okay, and that's what it looks like. I don't know why I didn't back up and get a picture of all 4 of them, but I didn't. And then there's a tag. I don't think that tag was off necessarily these, but it was off of the Ingersoll Rand that you saw previously. And I think it's pretty good to assume the same orifice size. So we're 7/16 of an inch on the orifice. Okay, so that's the end of that. Now we'll get on to the gory details here. I'm going to put myself back up here, I think. And let's see. Okay, so we went through, I guess we went through all of this. Oh, I know what I need to show you. So to get the leak rate through different orifice sizes, this is, and I'll send you, comes from Bill Scales. So this is just discharge of air through an orifice, different orifice sizes at different pressures, gauge pressure before the orifice. And so you see they don't have a 7/16. So they've got from 1/64 up to 1, but they don't have a 7/16. So I took these data points right here, the orifice size, and these flow rates, and used all of that information at 90. That's what I'm swagging as the pressure. They're typically a little above that, but there could be some back pressure on this thing, and I don't want to overestimate it. So anyway, I took this row of numbers right here and then took it to my Excel sheet and input it here. And then, of course, if you read the Excel sheet, these are the numbers that I'm sorry, if you read the table from Scales, these are the numbers that come out. directly out of the table, but if it's a sharp-edged orifice, you're supposed to take 61% of it. Again, I don't want to over project this thing, so I've taken 61% of this and put it in this column, and then I have fit this curve. If I can get over here to it. Yeah, there you go. Using this as the X and this is the Y, and then I did the curve fit. There's the equation of the curve fit, and the R squared is 1, so it's a perfect fit. And then this is 7/16, so I put it into the curve and it projects. And this is with the 61% flow coefficient. So it's coming out of this column right here. It just kind of does the, because see, it's not linear. You can't just, well, I guess you could do an interpolation. It wouldn't be. Anyway, I went ahead and did the curve fit. I think it's a little bit better. So I'm getting 176.6 CFM. And then I'm down here to further calculations. So this is the drain trap information. So for, and that should say timed, I can't type, for timed drains manifolded together, each set to blow 10 seconds and then be off for 30 seconds. Total cycle time is 40 seconds. This means one trap blows 25% of the time. So I've got 4 of them. So that should be equivalent to 1 blowing continuously on average. 7/16 inch orifice. I showed you pictures of the tags and all that. I've assumed the pressure to the traps is 90 psig. So there's where I actually do the calculation, is right here. Well, I guess I just punched the number. Sorry. Anyway, that's a number. The rest of this is text. And then from my using the sharp edge coefficient of 0.61. Thus, with 4 traps, we're constantly venting for 176.6 CFM. Okay, so then I just do the amount. So I take E35, which is this number, times 8760 hours per year times 60 minutes per hour, divide by 1,000. And so we've got 92,821 units of 1,000 cubic feet per year. Savings, I'm just going to use this number right here, 0.11 times that. That should be, what is that, E39 times E25. Yep, that's E25. Estimated cost, oh, I meant to put 1,500, there we go. And so, you know, you could put 2,000. I mean, it doesn't matter. It's a 1.6 month payback at 1,500. So I think that's about it. I will send you all of this. I'll post this video on YouTube, send you the link to it. And so I guess you guys should go ahead and write this up. If you have any questions, you can email me and I'll get back to you as soon as I can. So I hope you guys are having a great weekend and staying safe. And I'm sure we'll be in touch soon. Bye-bye for now.